Hello and welcome. My name is Tom Olson. I work for ARM and I'm chair of the Vulkan Working Group. I'm mostly here to talk about Vulkan, but I'll start with a word or two about other Khronos graphics APIs, particularly the OpenGL family and how they relate to Vulkan. I'll take a quick look at Vulkan adoption and use, and then dive into what's new, focusing on Vulkan 1.3 and the new profile system. I'll close with a medium deep dive into pipeline creation, which is a problem for many Vulkan developers, and explain some new features and extensions which are intended to help. We'll start with a little history. In 1992, 30 years ago, Silicon Graphics created an open standard 3D graphics API called OpenGL and founded an industry consortium called the ARB to manage it. 10 years later, the Khronos group created a mobile version of the API called OpenGL ES. After a while, the ARB joined Khronos too, and OpenGL became a Khronos API. Both APIs were very successful, and by 2012, OpenGL ES was shipping in over 1 billion devices a year, but there were problems. The APIs had diverged over time and were not compatible. Also, the architecture of OpenGL was 20 years old and no longer matched the underlying hardware. The two working groups decided to work together on a new API which would solve both problems. Internally, it was called GL Common because it was meant to be a GL for both desktop and mobile. But because it was very different from OpenGL, when it was released, it was renamed Vulkan. Although Vulkan is descended from the GL APIs and is based on the same underlying computational abstraction, the design philosophy and the APIs themselves are very different. OpenGL presents a very high-level abstraction, which is single-threaded, synchronous, and much simpler than the underlying GPU. Supporting this abstraction with decent performance requires a large and complex driver, which does things like dependency tracking, memory management, synchronization, error checking, and high-level shading language compilation. It makes writing application code easy, but the driver is CPU intensive and hard to reason about, which makes debugging performance problems difficult. And because the driver doesn't know what the application is trying to do, it has to guess, which doesn't always go well. In Vulkan, you get a messier and more complex abstraction, which looks more like the hardware. Most complex functionality is moved out of the driver, so the driver can be small, simple, and predictable. Shading language compilation moves offline. Error checking moves into software layers, which you use only during development. And things like dependency tracking, memory management, and synchronization become the application's job. So the application has to do a lot more work, but because it knows what it's trying to do, it can do it better and potentially get better performance and lower power. Which API is better? It depends what's important to you. If ease of programming is a top concern and you don't need multi-threaded rendering or hard real-time performance, OpenGL is a good choice. If you want minimum CPU load or multi-threading, and you expect to spend a lot of time on performance tuning, I would recommend Vulkan. So let's talk about Vulkan. I'll start with where and how it's being used. Vulkan is supported by all of the serious GPU vendors except Apple on hardware ranging from mobile devices to workstations and servers. It's available on Windows, Linux, Android, 2 streaming platforms, SteamOS, and Switch. And although Apple does not support Vulkan officially, you can run many Vulkan applications on macOS and iOS using the Molten VK shim layer. Many commercially important applications use that approach, from games like Dota 2 to engineering tools like Autodesk Fusion 360. If you prefer to work through a third-party game engine, pretty much all of them now have Vulkan rendering paths. And in many cases, that path is the default, at least on mobile devices. Speaking of mobile devices, Vulkan was slow to come to Android because it's so hard to get driver updates. but as of March of this year, Vulkan is on almost 3/4 of active devices. I'm quite sure that Vulkan will be on more than 80% of Play Store devices by the end of this year. As to what Vulkan is being used for, the number one use case, of course, is games. Counting them is a bit tricky, but we know of at least 348 Vulkan games on desktop. The fact that Vulkan is the preferred API on Stadia has, of course, driven a lot of use. On mobile, Vulkan is the API of choice for games which are performance sensitive or are targeting higher-end devices. This includes very high-profile and commercially successful games like Roblox, Fortnite, and Genshin Impact. Vulkan is also used in some important non-game applications, including Autodesk Fusion 360, which I mentioned earlier, and Adobe Premiere Rush for video editing. Recently, Video has also announced a 3D scene editing tool called Substance 3D Stager, which includes a full path tracer written on top of Vulkan ray tracing. Turning now to what's new in the API. In January, we released Vulkan 1.3, our fourth major release. With 1.3, we're doing something different from what we've done in the past. So before I describe its features, I'd like to talk about how older versions were constructed and what is different now. When we designed Vulkan 1.0, we set the minimum hardware requirement at OpenGL ES 3.1 so that the API could be supported on both advanced mobile hardware and 5-year-old desktop hardware. We did this because an API that only runs on the newest hardware is not useful to developers. We included a few more advanced hardware features, but we made them optional. With later versions, we kept the same hardware requirement. When we added software features, we made them mandatory, things like timeline semaphore. But when we added hardware features, we had to make them optional because not all hardware could support them. The problem with this is that over time, we had more and more optional features in Vulkan Core, and this led to fragmentation. Every implementation had different capabilities. We had to do something about it. What we've done in Vulkan 1.3 and plan to do going forward is this. We'll keep the hardware requirement at ES 3.1 so that all implementations can support the new API. When we have new software features that every implementation can support, we will make them mandatory in a new core version. We'll add new hardware features only if all implementations can support them. Most, if not all, features of new core versions will be mandatory. We'll introduce a system of market-specific profiles to capture requirements that go beyond what the core version provides. When we have new features that we think every implementation in a specific market should support, we will make them mandatory in a profile for that market. The only optional features will be extensions. So now we can talk about Vulkan 1.3. It promotes 23 extensions to core. Here I've grouped them by the kind of functionality they provide. I won't talk about all of them, but I'll point out a few highlights. The list starts with extensions to help pipeline creation and management, which developers tell us is a huge problem. Because it's so important, I'll come back to it later in the talk. In the ease of use category, there are two features that have a big impact on how you use the API. Synchronization 2 makes Vulkan synchronization easier to understand and less error-prone. Dynamic rendering lets you draw without using render pass objects or subpasses, which makes it easier. Unfortunately, it also disables some optimizations which are important on mobile, so you may not want to use it there. We're working on a fix, and when we have it, you'll be able to use dynamic rendering everywhere. Two features that were optional in Vulkan 1.2 are now mandatory. Vulkan Memory Model allows you to take advantage of implementation guarantees about memory access behavior. Buffer device address gives you some of the functionality of pointers. The only completely optional features we added in 1.3 are a couple of image formats. Implementations are not required to support these. The reason we included them is so you can query for support without having to enable an extension first. Along with Vulkan 1.3, we introduced Vulkan Profiles. A profile is a formal specification of minimum capabilities across a set of Vulkan implementations. It defines a minimum core version, a list of required features, properties, and formats, and a list of required extensions. It's like an alternate version of the core specification, which has additional features and stricter requirements. Profiles are outside the Vulkan specification. Whether a profile is supported by a given implementation depends only on the API version, features, limits, and formats it exposes. This means you can write new profiles that describe the functionality of old devices. Along with the profile mechanism, we released two profiles. KHR Roadmap 2022 captures functionality that we think will become universally supported in mid to high-end devices targeting smartphone, tablet, laptop, console, and desktop markets starting in 2022. I won't list the features, you can find them online, but it includes at least two which really change the way you design your applications. One is descriptor indexing, which gives you bindless access to resources. The other is guaranteed support for subgroup operations in fragment and compute shaders. We call this the roadmap profile because these features are part of our roadmap. All Khronos member IHVs who target these markets have committed to supporting these features in at least some products they will release in 2022 or soon after. The other profile is Android Baseline 2021, which has a different character. Where the roadmap profile describes features we expect to be widely available in the future, this profile describes features that are widely available today on Android. Software developers who target this profile should be able to reach a large majority of devices that are active on the Play Store. Google tracks support on the Android developer dashboard, and as of March, 68% of devices supported everything in the profile. But if you leave out one feature, Shader Image Gather Extended, you can reach almost 83% of devices. We released Vulkan 1.3, the conformance test, and basic shading language support in January. You can get conformant drivers today from all three desktop IHVs and from the open source RADV project. ARM and Imagination have demonstrated conformant mobile drivers, though I don't know if they are available yet in consumer devices. There's also a 1.3 SDK from LunarG, and there is support in RenderDoc. I don't have time to do justice to the 1.3 SDK, but two headline features I want to mention. First, the SDK provides beta tooling for working with profiles. There's a JSON schema for specifying profiles, a header-only library that lets you check for and enable profile support, and a layer that helps you validate that your application doesn't use anything beyond what the profile provides. That layer replaces the DevSim layer if you're familiar with that. Second, the validation layers now provide fine-grained locking instead of taking global locks. This provides more than a 2x speedup in most of the titles LunarG tracks. In earlier SDKs, you had to turn it on manually, but the plan is to enable it by default in the June SDK. As I said earlier, developers have told us that pipeline creation is a huge problem. There are features in Vulkan 1.3 that provide some help, and we have a new extension which provides more. I'll spend the rest of my time talking about these. First, just to remind you, in older APIs like OpenGL, you do all of your drawing relative to a context, which contains the state of the graphics pipeline. To change a piece of state, you call a function. So the render loop of your application looks like set some state, draw, change state, draw, and so on. This is nice for the application because the state appears to be orthogonal. You can change any piece of state anytime without affecting anything else. But this is an illusion. After a state change, when you say draw, the GL driver does what we call state validation, where it looks at all the state and translates it into GPU commands. that can be very CPU intensive, and it has to be done in the render loop, so it can easily lead to dropped frames and hitching. OpenGL drivers do all kinds of magic to try to hide the problem, but they do it by guessing what the application is going to do next, and when they guess wrong, bad things happen. This was one of the key motivations for modern APIs like Vulkan and DX12. In Vulkan, there is no global context. Instead, state is recorded into command buffers, potentially in multiple threads. But instead of setting state directly on the command buffer, you bundle the state you need for a draw into an object called a pipeline, and you're supposed to create your pipelines as early as possible. So your render loop becomes bind pipeline, draw, 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 bind pipeline, draw, draw, and so on. When it works, it's super fast and everything is wonderful. But creating pipelines still requires state validation, which is still expensive. So everything depends on being able to create pipelines efficiently and early before you need them in the render loop. Unfortunately, that turns out to be really hard. Sometimes you just don't know what state combinations you're going to need until you need them. So you may have to create pipelines during command buffer recording. It helps that Vulkan supports pipeline caches, so you never create a pipeline more than once. Vulkan also allows saving pipeline caches to disk and reloading them the next time you play the game. But if you do get a cache miss, it's very expensive. Cache misses are also unpredictable. When you call create graphics pipelines, it might be fast, or it might take 100 milliseconds. Even initializing the cache is hard. Some game engines create hundreds of thousands of pipelines. What can we do? One thing that helps is to create fewer pipelines. And one way to do that is by using dynamic state. That is, state that you set on the command buffer during rendering, like in OpenGL, instead of putting it in the pipeline. Unlike OpenGL, Vulkan only allows state to be dynamic if the implementation can treat it as orthogonal and use it without significant cost. Vulkan 1.3 promotes 2 extended dynamic state extensions to core. That adds 15 pieces of guaranteed dynamic state, including very commonly toggled state, such as cull mode. Another thing we can do is to reduce the number and cost of cache misses. A lot of engines try to make sure that all the pipelines they need are in cache, either by creating them during startup or by loading a pre-built cache from a remote server. But how do you know whether the cache is fully populated? EXT pipeline creation feedback lets you find out during gameplay whether a newly created pipeline was a cache hit or not. You can feed that back to your build system to improve your pipeline cache coverage. Another extension, EXT pipeline creation control, lets you tell the driver, if you don't find this pipeline in the cache, don't create it. Just fail quickly and return null handle. When the application sees a null pipeline, it can use some kind of fallback. For example, a slow Uber shader that can draw anything. So it can keep drawing without a hitch, and at the same time create an optimal pipeline on a background thread. Both of these extensions were added to core in Vulkan 1.3. In March, we released a new extension, KHR Graphics Pipeline Library, which builds on the idea of a fallback pipeline. It partitions the stages of the Vulkan graphics pipeline into 4 groups and lets you create partial pipelines for a subset of those groups. To create a pipeline for a group, you only need the state that is relevant to that group, so you don't have to know what state combinations you're going to need. In the render loop, if you get a new combination, you can ask the implementation to do a fast link and give you a pipeline very quickly. A fast linked pipeline won't be optimal, but because you get it right away, you can keep rendering without a hitch while you create an optimally linked pipeline on a background thread. When it's ready, you can delete the fast linked pipeline and use the optimal one instead. Implementing this extension involves a lot of compiler work, and right now I believe it's only supported on NVIDIA and possibly in the Mesa stack, but it is coming everywhere. For more information, Chris Glover of Google has a webinar presentation that goes into detail about how the extension works. There's a great blog post by Dan Ginsberg of Valve talking about how he applied the extension in Source 2. And recently, Sasha Willems contributed a code example to the Vulkan samples repository. We're very excited about Graphics Pipeline Library and looking forward to your feedback. That's all I have. Thank you for your attention.